Okay, we are going to talk about vectors. Okay, if you've taken physics, you've probably already been thinking about vectors. They're very useful in physics especially, but in all kinds of applications. So here's the idea of a vector. It represents a magnitude and a direction, okay? So things like speed, like motion, right? So you're going a certain speed in a certain direction, you can represent with a vector. You can also represent growth of anything in two dimensions. But the main application that we'll talk about is, or that you'll probably first encounter, is speed and direction. So it's a directed line segment with an initial point and a terminal point. Okay. Vectors are identified by magnitude, which we represent by the length of the line. So a longer line means more speed or whatever it is that you're measuring. And direction, represented by the arrowhead pointing toward the terminal point. Okay, so like for example, this is a vector. Here's our initial point C, our terminal point D, and we always put a little arrow at the end to show us which way the line is pointing. The position vector has an initial point at 0, 0 and is identified by its terminal point AB. Okay, so this point is AB, and you'll notice they have these little, sometimes we represent them with these little kind of pointed parentheses. So here are different ways that we refer to vectors. So usually it's the letters we generally use are V, U, and W. A lot of times they're bold, and if it's not too much hassle, we usually put a little arrow over them. Okay, if you're just typing in something and that's kind of a pain, then we don't worry about it. But little arrow over it means you've got a vector. And the arrow is always pointing to the right. Doesn't matter which way the vector is pointing. Sometimes you represent it this way. So if we have an initial point P and a terminal point Q, we could write PQ and a arrow, over them. Or like it referenced above, we could use these little kind of pointed parentheses and our terminal point. This indicates that the initial point is at the origin. So something important about vectors is it doesn't matter where they are. Okay, we can pick one up, slide it around, move it up, move it down, move it to the right, move it to the left. So these two vectors, CD and this vector AB, are the same vector. Okay, all that matters is the length of the line and the direction that it's pointing. So you can see that none of that really matters where it starts or where it ends. Okay, it's the length and the direction that determine a vector. So we can take any vector and kind of scoot it over until it is, the initial point is at the origin to make it a position vector. Okay, so these are the same vectors. They're just plopped down on the Cartesian coordinate plane in a different place. All right, so let's do an example. Find the position vector. So they tell us it starts at 2, 3, and the terminal point is 6, 4. Find the position vector. Okay, so in our mind, we can just imagine, okay, what happens if we scoot this back and this point is down here at the origin? So you can see, just looking at this, we can say, well, what is the x component? Well, we can say 1, 2, 3, 4, 5. And they put this in the wrong place. This is actually supposed to be right here. So please ignore the mistake. Pretend this point is scooted right back there. So actually the x position is 1, 2, 3, 4 over and 1 up. Right? So just graphically, we can look at that and say, oh, it's going to be 4, 1. Right? We could also just say, well, it's going to be the x component of the terminal point minus the x component of the initial point, terminal point minus initial point for y, and there's our vector. Not anything really tricky going on here. So find the position vector given they give us an initial point and a terminal point and graph both vectors in the same plane. Okay, so to find the vector, we'll say, okay, the x of the terminal minus the x of the initial, we get 7. Y of the final minus y of the initial, we get 3. So here's our position vector, and we can draw them both on the same plane. So here's negative 3, 2, terminal point 4, 5, initial point 0, final point, or terminal point 7, 3. And you can see it's just as if we scooted it down and over to the right a little bit and got our position vector there. find the components. So what if we want to go the other way of a vector with initial point 3, 2 and terminal point 7, 4? Is this the same one? Nope, not the same one. Okay, so first we want to find our position vector. Okay, so we'll say, okay, 7 minus 3, 4 minus 2. Here is our position vector, right? And now there's really not much else we need to think about. We can say that, well, the components are 4 and 2. And we could even think of, we'll talk about this in a little bit, we could almost think about, here's one vector and here's another. And if we kind of added them together, which we'll talk about how we add vectors in just a minute, we're going to get our position vector B. All right, so magnitude and direction. So if you have a position vector, we might want to know how long it is. And the way we talk about that for vectors is the magnitude. We represent that like this with like absolute value signs around the vector. And you can imagine if I said, what is the length of this line? You say, aha, I'm just going to make a right triangle and use the Pythagorean theorem. So it's a squared, the square root of a squared plus b squared, right? This is just using the Pythagorean theorem to find how long the hypotenuse is. The direction we're asking is, what is that theta? So just like everything this year, for direction, we're always starting in the positive x direction and moving this way. So we're looking for what that theta is. So that's going to be, so tangent of theta is going to be b over a, or so inverse tangent will give inverse tangent of b over a will give us that theta. Okay. So two vectors are considered equal if they have the same magnitude and the same direction. Or another way to think about that is if they both have the same position vector. Okay, it doesn't matter where they are on the plane, it just matters if they have the same magnitude and direction. Okay, so what if we have this question? Find the magnitude and direction of a vector with initial point, negative 8, 1, final point, negative 2, 5. So first let's find the position vector. So minus 2 minus negative 8 gives us 6. Negative 5 minus 1 gives us negative 6. Did I say negative 6 here? I meant 6. So here we are. Here's our position vector, 6, negative 6. There's our vector. Okay. So to find the magnitude, we can make a right triangle here, and each side is 6 long, so it's going to be the square root of 6 squared plus negative 6 squared. We can simplify, it's going to be 6 square root of 2. And now we find the inverse tangent of b over a. Right? It's inverse tangent of b over a. So the inverse tangent of negative 1 gives us an angle of negative 45, and just as we have been doing, if we're in quadrants 1 or 4, we're good. If we're in quadrants 2 and 3, we've got to do a little bit more thinking, as we have with polar coordinates, right? So quadrants 1 and 4, things are pretty easy. We literally just find the inverse tangent. Quadrants 2 and 4, we've got to think through things a little bit and interpret what the angle is that they gave us.